Yes, it's working. Thank you.
Yeah, okay. All right, so I'm going to share my slides right now. And can everybody see my screen right now?
Yes.
Looks fine. Okay. So let's start with a very brief recapitulation of what we did last week. So last week was a feedback linearization. It's a technique where we actually have a nonlinear system. We started with this tank here. And then by applying a nonlinear state transformation and a nonlinear transformation of the input, we finally arrive at a linear system. And then all the nice theory of linear control theory can be readily applied in the linear world. And then we have to, obviously, we have to transform it backwards to the nonlinear world. So it gives us a nonlinear control law for a nonlinear system, resulting in linear system behavior. Let me just very briefly recap how we did it. This is the kind of system that we consider. It looks a little bit strange that we have the input U appearing in a linear form. We call it the input-defined system configuration. And as I told you last week, almost say 95% of all systems that I encountered in control theory, which I do for the last 25 years, have that form. Only very few and nasty systems don't follow that form. And then mostly there are also workarounds to get it back to this form here. Very important to note is that the transformation, the way we transform the system depends on the chosen output. So you might recap from the linear system theory that with feedback control, Ackermann formula, it only depends on the state vector and then the input. In this case, the transformation essentially depends on the output. So for any system that you choose, you might want to change the output that you want to control. So for example, with this tank system, obviously that it was only about to control the level here, the level, fill level. You might also choose to control the amount of outflow here. And then the whole control might look differently. And this is the case with all systems. And you will see today that the choice of the output determines whether we are going to get into trouble probably or not. So in this case, what did we do in order to get the transformation? We took the output Y and we applied time derivatives in a consecutive fashion. So we took Y dot, Y double dot all the way. So the transformation looks like this. So our new state variables are C1, C2, and so on. And there are Y, Y dot, Y double dot all the way through the n minus first derivative. We have a strange expression here, which is LF, which is the lead derivative. It looks a little bit strange, but it's only a kind of workaround, a tool for all those expressions not to look too complicated. So if, for example, we take the output Y, which is h of x, then Y dot is LF h of x. So it is, in other words, simply the derivative of h, which is probably a gradient vector along the vector field, which is f here, okay? So in other words, this is from last week. So Y double dot is the time derivative. Let's probably start here. This is easier. So we take a certain function C of x. If you remember, I expressed it, for example, as the temperature in the room. So this expression here would be the gradient. This is a vector pointing in the direction of maximum increase, okay? And A of x is the vector field. So it might be the flight path of a bee flying along in your room. So this product is actually the change in temperature, the temperature time derivative the bee expresses as it flies along your room. So this is the abbreviation of this lead derivative, which we use. It's also often used in fluid mechanics, and I mentioned this last week also. So we use this. And by doing this, first of all, we have the state transformation. And for the moment, we probably don't see any use of it. However, if we take the time derivatives, as we do here, we see very simply C1 dot is simply C2. C2 dot is equal to C3. So what we see here is that each of the state derivatives is simply another state. So it gives us an almost linear system. I mentioned last week that we're actually ending up with a chain of integrators. However, there's one thing which is still in our way. And this is the last derivative, which looks like this. So it's still non-linear, those non-linear derivative functions. And we simply overcome this by assigning this expression here a so-called synthetic input, which we call V of t. So V, first of all, it's equal to the highest derivative of the output. So the nth derivative of the output. And then we set it equal to this expression. And this is the second transformation, if you want so. The first transformation applies to the state, which is given here. The second transformation applies to the input, which is given here. And with this, we finally end up with this chain of integrators. So the nice thing about feedback linearization is that eventually you're always ending up with the same system, which is a chain of n integrators. And with this, you can do all the control design that you already know. For example, Ackermann, we used this last week. You have the Ackermann formula with the coefficients. So you choose a desired closed loop polynomial, which is essentially linear dynamics, I have to point out. And then once you have the control law, you see the control law depends on C, on our new transformed states. Of course, obviously also on the reference value. You insert into this expression here. So this is our backwards transformation that tells us what the actual physical input U should be. This is in a nutshell, what feedback linearization is about. Of course, there are some ways how to express C in terms of X or vice versa. So everything can be done here. This block diagram, again, explains what we are up to. So this is a nonlinear system. And then our control law, which is essentially this one here, comprises two parts. This is the feedback part. So it comprises nonlinear feedback in terms of X and linear feedback in terms of C. And of course, between X and C, there's this transformation. So they're more or less can be expressed by each other if you want so. This is one part. Then the second part is the feed-forward part, which is here. And all in all, what you can see here is a nonlinear control law. It's obviously nonlinear, applied to a nonlinear system, resulting, as I expressed it here, in a linear system behavior. So the overall input-output behavior is linear, okay? And if you just tracked everything that I said today, for everything to work here, it depends on the fact that we have the so-called full relative degree, so that the input of the system does not show up in any of these derivatives. Okay, so we assume that all those derivatives with respect to the input, which you see here, do not show up only in the nth derivative. So theta, which I indicated here, is normally the so-called relative degree. It can be equal to n, to the system order, or it can be less than the system order. In last week's lecture, we discussed systems with full relative degree, like this one. And now today, I'm skipping everything that we did last week. Today, we are considering, hopefully you did also have some fun with the motorcycle and played around. And I think it's very important to just use the MATLAB files that we sent you and really play around by yourself, just to get a grab on all those expressions, how to apply them, what happens if you make a mistake. So you normally also learn by mistakes. So I really recommend that you use these files, okay? So today, we are treating the more difficult and more involved case. And this is the one where the relative degree is less than n, which is expressed here. So again, what we do is we start to take the output, which is h of x. So y obviously is equal to h of x, okay? And we continue to carry out time differentiation. So we do this, we get C2, C3, all the way through C theta. And in C theta, by assumption, we assume that the derivative also shows the input. Let's take a look at this. Before we do it, of course, the whole problem that we have to face is we have to find a state transformation. So C is equal to T of X. Also, of course, we want to know the inverse. So what is X if we know C? And of course, for this purpose, we have to compute the inverse transformation. And both the forward transformation and the inverse transformation must be continuously differentiable, okay? And if this is the case, then we have a so-called diffeomorphism, which I already mentioned last week. Okay. So if we do as I just described, so we just carry out those differentiations and Lie derivatives. And of course, at some stage, at some derivatives, at some order, we have to stop, okay? Because if we carry out the differentiation, then obviously, let's start from the beginning. C1 dot, that's y dot, is equal to LF h of x, which is y dot. So we continue with the same pattern as last week, all the way through the derivative, the time derivative of c theta, as you can see here, because obviously here, by definition, the input shows up. So we assume by definition that LG, LF, theta minus 1, h of x is different from 0. Okay, that's what we assume. And then we see that we run into some kind of difficulties because the pattern that we applied last week cannot be continued because there are some other transformations, I just mentioned them here, which are still unknown. So we are left with theta plus 1, theta plus 2, all the way to n transformation functions that we don't know. And without knowing them, we cannot go on. This is our problem. Also, what we see is, before we actually turn to these transformations, we see that obviously still C1 dot is equal to C2. C2 dot is equal to C3 all the way through C theta. C theta dot is equal to this expression, which is similar to the one that we had last week. So you see essentially still for one part of the system, we get linear dynamics. Or to be more precise, we get a chain of integrators. However, this chain does not have the length of n as we had it last week, but it's only theta. Okay, and then with the last derivative, we get something, and obviously we are going to replace this by some virtual input, which we are going to do next. However, we are still left with the problem, what are we going to do about these guys? So this is the open question. Okay, and obviously, if we want to determine this transformation, and I just say it before we go into the math, this is really nasty. So whenever it comes up, normally we are in some kind of trouble. And let me just show you how this works. If we assume that we have some of these transformation functions, we have found them by some way, okay, then how do the time derivatives look like? Because obviously we will also need them here in order to compute the new system dynamics. And if we do so, then we can actually proceed in exactly the same way as we did last week. So, for example, the time derivative of the transformation number I, which is given here. So that's because this depends only on x. So that's obviously the gradient of this transformation with respect to x times x dot. And then if we insert the right-hand side of the state differential equation, which is here, we get something like the gradient of Ti times f. And if you remember the definition of the Lie derivative, this is nothing else but the Lie derivative of Ti along f. So it's denoted by LF Ti. And then we have something else, which is the gradient of Ti along G, which is LG Ti. Okay. And obviously, as you can see here, in general, any given choice of transformation that we might have made will take us to the situation where the transformation does not only depend on X or on C in any way, but also on the input, which we normally don't like. So I just underline this. We normally don't like transformations which also depend on the input, because you might imagine if we have a control law, then the control law will go into here. And as the control law depends on this transformation, as you've seen before, we get some kind of algebraic loop or a hen-egg problem. The control law must be determined by knowledge of this transformation, but in order to get the transformation, we have to know U. And this is normally nasty. It can be overcome. I'm going to show you something later in this lecture, but normally we will try to avoid it. And in order to do so, we try to take this guy here and set it to 0. And if you take a closer look, then obviously this is the derivative of Ti with respect to x1 times g1. So I just spell out what we have here in short notation. So that's the derivative of ti with respect to x1 times g1 plus the derivative with respect to x2 times g2 and so on all the way, and this is set to 0. So this is still a nasty differential equation because it's a partial differential equation. Ti depends on all the elements of the state vector. So these are n elements, 1, 2, 3, 4, 5, n. And this is a partial differential equation that has to be solved in order to get the transformation. And on top of that, we also have to ensure that this transformation is continuously differentiable, and the inverse function must also exist and must also be continuously differentiable. So this is all not so nice and not so funny unless you are really a fan of partial differential equations. I'm not, but I'm going to show you some way how to solve this later on, okay? All in all, what we are left with, let's turn back to this equation here is, we have a chain of theta integrators where the derivative, the last derivative, still depends on this guy. And as we did last week, we still take this here, it is denoted by phi, so it's a function phi, which depends on c and u, obviously. And we still call this, if you want, so a virtual input, okay? Then there's a second part that we have to consider. First of all, this part of the dynamic system is a linear one. It's a chain of theta integrators. This one here depends solely of your choice of the transformation function. So I call this time derivatives q. I just omitted this. So the derivative of ti with respect to time, I call this q. And of course, without any closer inspection, we cannot say anything. And obviously, this will still be linear dynamics. This will be a non-linear dynamics. So it's very important to note. This is linear. And this is generally non-linear, okay? And then in literature, the first part, which is the linear one, is called the so-called external dynamics. The second part is called the internal part. So why do we get these names, or where do we get these names from? First of all, you can split up the differential equation in the following way. So this is given here. So the first part is the so-called internal dynamics and the external dynamics. And if you take a closer look at what happens here, I'm just winding back a little bit. If you take a look, you can see that, or if you remember that y, our output y, is simply C1, then you can see that the first part of this system, the linear part, simply contains y and its derivatives. And then, of course, we get C theta, which is the theta derivative of the output. And this is simply equal to our so-called virtual input. So what you can observe here is that our output y is not affected by this second part of the system. The second part of the system, obviously, is affected by the first part, but not vice versa, okay? So it means that in the dynamic system, the first part here, and this is obviously seen here again, the first and linear part of the system is seen in the output. So this is the reason why it's called external. So you can see it in the output, whereas the second part is the so-called internal dynamics because it's in the system, but it's not visible. It's not observable, to say this more precisely. And this is the reason why we call it internal dynamics. What you can do now for the control, and this is seen in equation 525. So you can see you can apply exactly, or almost exactly the same control law that we had last week. So for the virtual input, in this case, we call it, it's called phi. It's almost the same name. We apply the Ackermann formula. And then there's one difference to last week. And this is the order of the system and the order of the controller only applies to the external dynamics. So it only applies to a system of order theta. In last week's lecture, we had always a system of order n. Here there's a system with an order of less than theta, and you can see that with your feedback gain, you have a number of zeros, and they all apply to the internal dynamics. They all refer to the internal dynamics. So you apply a controller with an order of less than n. So this is very important to note, okay? And the control law by itself only refers to a feedback from this external dynamics. However, as you can see here, you still have the influence of x. So in the control law, the internal dynamics also have some influence. You don't see it directly, you don't see it in the output, but in order to control the output, you also need this so-called internal or hidden states. This is the more involved part of the system. So if you consider this control law and the feedback gain here, then all in all, you're ending up with a system that looks like this. The first part has more or less exactly the same structure as last week. So it's a chain of data integrators. And then you have a control law. You use Ackermann's formula to assign some eigendynamics, some poles if you want so. Then there's the reference value. And then on top of that, there's the internal dynamics. And you see, one thing is the internal dynamics are somehow driven by the whole state vector. So they are somehow also excited by this external dynamics. Secondly, those states like C theta plus 1, C theta plus 2, all the way through Cn, they do not affect the output. So you could say, okay, let's just disregard them and forget about them. We don't need them. But this is not the whole story, because if you look more closely at the control law, which is here, you can see that they somehow go into the control law. So it might be the case, this is the dangerous thing in this situation, that you get a very nice behavior of the output. So the output follows a certain trajectory, but in order to do so, the input might grow or might grow to infinity. So you really have to care about the stability of the internal dynamics. This is very important. So it's also found here in the text, so to say. So again, here, I just mentioned this here, U depends on the internal dynamics. So you have to look after the internal dynamics. And if you look at the closed loop transfer function, so it's a transfer function between your W, your reference input, and your output Y, you see, first of all, again, it's a linear one, it's a linear transfer function. But even though the system has an order of n, the order of this transfer function is theta, so it's less than n, okay? Which indicates that there is a number of states which are so-called, so to say, hidden. So they are not seen in the output, they are not observable. You see, I've already highlighted this. They are not observable through the control law in the output, but they are seen in the control law itself. This is very important. So, and this is very, it's put in a box here. You have to check that the overall system is stable. So it means, first of all, you have to design a stable controller for the external dynamics, which you should already know. So you choose the proper coefficients of the characteristic polynomial, leading to a nice closed loop dynamics. But then you have to check separately if the internal dynamics are stable. And I'm going to give you some example on how this works, okay? So let's start by a simple example and an examination of the internal dynamics of a linear system, okay? So we're treating nonlinear systems in this chapter, but I thought it would be a nice idea to just start with a linear system, because this is going to give you the aha effect. So it's going to probably ring you some bell, okay? So this is a transfer function, okay? And this is the same transfer function expressed as a state space system. So you see, I used the controllability canonical form. You know it from preceding chapters. You only take those coefficients and then add them here. And you take the output and place it here. So it's just, it's done easily. And because the linear system is essentially also a special form of the nonlinear system, you can see obviously that our f of x, our vector field f of x, is simply this one here, okay? Sorry. So this is f of x, so it's very simple. And this is our g of x, which is constant. In this case, it's constant, okay? And obviously this is h of x, which is also linear in x, okay? So you can carry out all the Lie derivatives if you want to. I'm not going to repeat this again now. You should already know it somehow. Very importantly is we have a system of third order. It's a third order system. However, this Lie derivative here, it's Lg LfH of x, is 1, so it's constant. Obviously, it's constant, and it's always different from 0. Okay. And obviously, you can note that if you apply the Lie derivative formalism to a linear system, you always end up with expressions like C transpose times A times X, C transpose times A squared times X, C transpose times B, or C transpose times A times B. You always end up with these expressions. So maybe try this at home and just verify it. Obviously, we have a system with a relative degree of only 2. Okay, because this is always different from 0. So for the transformation, in order to get our transformation, this would be the first equation. So this is T1 of x, if you want so. Then we find the second transformation to be this one. So this is T2 of x, because we just follow our formalism. And then we are left with our T3. So we don't know what is our T3. And as I explained before, we don't, however we choose this T3, we still don't know how it should look like. We want it to be independent of our input, which means if we take the, so T3 dot of x, which is then T3 over Tx1 times x1 dot plus T3 times Tx2 times x2 dot, sorry, plus, so I'm not going to continue this, and this should be equal to 0. So what we do here, and this is a very nice, simple example for you to understand this, we choose, because everything is linear in the system, we choose our T3 to be a linear function of x, because we expect that since everything is linear, we can also expect that this will also be linear, okay? So what we are facing here is that T3 of x times our g of x, which is simply constant, it's here, should be 0. So if you look at this, then obviously any choice in T3, sorry, I forgot this is T3.1, okay. So any choice of T3.1 and T3.2 would actually satisfy this equation if you look here. So T3.3 obviously has to be 0, otherwise this will never be 0, and there are zeros here. So any choice here of these two guys will satisfy this equation, okay? And I chose it to be like this, 1, 1, 0. And it also has another meaning because our T1, which is here, T2 is here, we have to have a diffeomorphism. So all three together must result in a continuously differentiable function, and it must be invertible, okay? So all in all, if I just complete this, so C is equal to T of x. So it's equal to T1, just summarizing everything. T1 is 2, 1, 0 times x. T2 would be 0, 2, 1 times x. And thirdly, it's 1, 1, 0 times x. So obviously, our transformation is also a linear one, and you also find it here, okay? And obviously, by choosing 1, 1, this matrix, and I call this T, will also be invertible, okay? So T to the minus 1 exists, okay? Okay, so with this, of course, this is satisfied. And then we get out our system transformation. So C1 is equal to h of x, which is here. C2 is this. This is our C3. Also, we have the inverse transformation. Everything is neat and nice. And now for the time derivative, we get C1 dot. Obviously, it's C2. C2 dot. Now we have to take a look. C2 is C transpose times A times X. So C2 dot would be C transpose times A times X dot. And X dot, that will be, we still want to remain or to stay in the C world. So this would be A times T to the minus 1 times C plus B times U. And you can see we end up with this expression. So C2 dots obviously depends on all the C's, okay, and also on the U, okay? Now, if you choose the virtual input, as I mentioned before, just to be equal to the C2 dot, so it's equal to V, we would get some kind of control law, okay? So this the control input would be determined from this equation, okay? And from this, very simply, we get the external dynamics. External dynamics is simply C1 dot is equal to C2, C2 dot is equal to V. But that's not what I'm going to show you here now. This is just following the instructions given in the scriptum. Very interestingly, let's take a look at the derivative of the third state here. So C3 dot, okay? We see C3 is equal to 110 times X. So C3 dot is equal to 110 times A times X plus B times U, okay? And now again, we are going to express X by T to the minus 1 times C, and then you end up with this. So if we summarize everything that we got here, we see, first of all, this is the external dynamics. So we are able to steer the output or the second derivative of the output, because V is essentially equal to Y2 dot. So we are able to steer the second derivative of the chosen output. And then there's the so-called internal dynamics. You see, it doesn't show up here in the external dynamics. There's no way where we see the C3. However, C3 by itself is driven by C1 and C2. So obviously, if C1 and C2 follow some reasonable trajectory, so will C3. And then there's something interesting. We see there's some kind of eigendynamics. So C3 dot is equal to something, namely minus 2 times C3. And then there's one way to examine this, and this would be if C1 and C2, for example, are 0. So if we control the output to 0, then eventually C1 and C2 will be 0. And then the internal dynamics are also called zero dynamics, okay? Let me just underline this here. They're also called zero dynamics. And so we see in this example, C3 dot is equal to minus 2 times C3, okay? So obviously this is stable, okay? And this is no coincidence. It refers to our numerator, okay? In our numerator, we have a 0 at minus 2, and this 0 shows up as a pole of the internal dynamics. So I'm leaving you now with this example, and I'm giving you as a homework. Try everything again, and instead of S plus 2 in the numerator, try with S minus 2. So that would be a non-minimum phase behavior. And in German, we know it as Allpass behavior. So it's encountered in many systems. So try this, and then just check what is going to happen here. And this is a good homework. Now there's another example, and this is if you want, so theoretical one, which is only of like educational value, tutorial value, but it should show you what is happening in a system with unstable internal dynamic. What does it mean if we get unstable internal dynamics? So this is a fantasy example, if you want so. So you see x1 dot is equal to some expressions that depend on the state, plus u. X2 dot is equal to minus u, okay? And then we see that y, which is the output, is simply equal to x1. So without any further examination, I can already tell you this system has an order of n is equal to 2. And since our output is x1 and x1 dot already contains u, the relative degree will be 1. And of course, this is revealed by computing the Lie derivatives. So I'm going to leave this to you as a homework to do this. And of course, you can see already that LGH of x is equal to 1. So it's different from 0. So we have a relative degree of theta is equal to 1. Okay. So let's just follow the book. What is going on here? So C1, which is our first transformed state, is equal to y, which is x1. C2 dot is equal to y dot. And if we take a look at what this is, we find immediately that this is the right-hand side of this equation. So it's equal to this one here. And then if we follow the book, we choose this to be our virtual input V, okay? So again, we are able to control, we drive the first derivative of our output. Or in other words, so if we solve this equation for U, then we get this one here. This is our control law. So if we have a certain trajectory for our output Y in its first derivative, this will be our control law. And then the external dynamics. So this is what we see on the output will be this. So Y is equal to C1, C1 dot is equal to V, or more simply speaking, Y dot is equal to V, our virtual input. So we don't care about the input so far. Then we could choose this is a first order system. So we could choose a very simple control law like this one here. So V is equal to some minus Kp, which is a control gain, control constant, times Y minus W. So it's pretty much like we did with this very first example with the bowl of water, so to say. If we take this, insert it into here, we get this one here, this guy here. So if Kp is greater than 0, then this is obviously going to be stable. So we are happy, and we're going to run this controller, and everything is going to be nice and neat. Well, the answer is no, this is not going to happen, because what we have to do is, we take this guy here and insert it into this equation, and then take a look at the control law. Or we can do it the other way around. You can choose to do this at home. The other way would be, examine what is going on in the system. So x1 dot, which is equal to V, which shows it that way. This is our control law. x2 dot, which is equal to minus U. So this is the way, this is the point where the control law is inserted here, is equal to this. And if you insert the control law like this, you end up with this expression here, okay? So you can see, in some way, if we control, for example, W to be 0, so if we control the output, if we want the output of the system to be 0, then obviously x1, which is our output, goes to 0. And then we're left with a very simple equation. x2 dot is equal to x2. So this is an unstable equation, an unstable behavior. So x2 of t will be equal to x2 0, some initial condition, times e to the t. So it's growing exponentially, okay? And then you're going to see that also our control law, you find it here, if x2 grows exponentially, then even though x1 goes to 0 and v goes to 0 because the control error goes to 0, the control input goes to infinity, to minus infinity, okay? So that's the downside. So you always have to look at the internal dynamics. You can find it out if you simply solve for x, for example. And of course, also in this example here, it's chosen such that the internal dynamics is still, the zero dynamics is still linear. And obviously you can see it's driven by the external dynamics. So it's driven by x1. And depending on what x1 does, you might drive x2 somewhere. But even if x1 and w, of course, if they all go to 0, you're left with this guy, and then it's a problem, okay? Okay, so this is, if you want an adverse example, it should warn you that you should not trust everything, and then you should check everything. Now there's a nice example, and it's a good one, because like 51 years ago, we managed to land on the moon. And as I told you last week, whenever you start a rocket, or if you want to land a rocket, you have to deal with this problem. So you probably know that SpaceX, it's a very famous American company. They are nowadays already able to actually land rocket stages. And with each of these maneuvers, you have the problem, and you can see it here, that you normally propel the spacecraft by exhausting some hot gases. They are normally leaving your jet, so this is the jet here, at some velocity. And then, of course, the whole spacecraft is governed or controlled, described by the impulse balance. And it's the momentum balance with variable mass, okay? So you can see this here. This is the differential equation. I'm not going to derive it, but I would probably ask you to do this yourself. So this is a the momentum balance for systems with variable mass. So you see, you actually have two states here, or maybe even three. So this is the height of the spacecraft. So this is the acceleration, the vertical acceleration of the spacecraft. And then you have a mass m, which depends on t, because obviously as you burn up fuel, as it's exhausted here, you lose mass. I told you last week, in a normal rocket launch, 95% of the mass is actually exhausted. So only like up to 5% is actually the useful payload. So it's really important to consider this. And then you can see here, this is the m dot. This is the amount of mass, so like kilograms per second, which is exhausted here at a velocity, at a relative velocity of vg. So this obviously, this is the impulse, that is the force that is applied on the spacecraft and lifted, okay? And this, of course, this is the pull of gravity. So this is the equation. If we summarize it, we have to choose three states. Obviously x1, which is the height. So we want to control this height. So we want the soft landing on the moon. This is the vertical velocity. And of course, this should be 0 as we land. And x3 is our mass, okay? And then we have the actuating variable. If you want, so this is the change of mass. So you can assume that normally there's the rocket, there's the combustion chamber. You probably all know how it works. So there's a number of reactant gases entering the chamber, and you're able to control this, okay? And of course, the more mass, so the more fuel and the more oxygen go in here, the more mass flow you will get. And normally, this is a property of all those nozzles, you get a constant exhaust speed. So this is a so-called Laval nozzle. You probably know this from fluid dynamics, that the exhaust speed is more or less constant. And obviously, of course, the higher the exhaust speed, the better, because the less propellant we have to use in order to lift the spacecraft. Okay, so all in all, what we get here is a third order differential equation, which you can see here. It's given here. So our output again is x1, it's the height, our altitude if you want so, and this is our differential equation. So you see, all in all, it looks pretty nice, and there's only one non-linearity, which is this one here. So you see, this is u divided by x3. This is the only non-linearity that we get in the system, okay? So again, we play the game of the Lie derivatives. I'm not going to show it to you again. Maybe just try it yourself at home. It's really good to get acquainted and to get somehow related to all those equations and how to familiarize yourself with it. All in all, what we get here is a relative degree of 2. So this system has an order of 3, but a relative degree of 2. So we have to check what happens here in this system. This is something I'm going to show you in a minute. So all in all, what we get here is C1 is h of x, which is x1. C2, which is the derivative of x1, which is h dot. It's obviously x2. And then we are left with these nasty third transformations. We don't know how to go on because we cannot continue. So the only thing we want is, once we have chosen our transformation, we want the Lie derivative, so the gradient of t3 along g, to be 0. So we don't want the time derivative. I just repeat this here. So t3 dot of x, which is equal to t3 of x. So that's the gradient of t3 times, let's say, f plus g times u. So obviously we want this product, we want this to be 0, okay? So if we spell it out, and I'm going to do this here, and because you see here, the first component of our g vector is equal to 0, we only have to care about the derivative along x2 and x3. So let's take a closer look. So that's the derivative of t3 along x2 times this product here minus this derivative times 1, so to say, because this is, take a look, this is just simply minus 1, so it's a simple example. So here we are. This has to be 0. And if you take a closer look, you can see that this is actually a partial differential equation. So T3 obviously might depend on x1, x2, and x3. And we see that the derivative along x with respect to x2 and x3, there are in some relation that has to be satisfied, okay? And this is normally done. So with, say, 97% of all those problems that we have here, it's solved by the method of characteristics, of characteristic curves. And how is this done? I'm just explaining it very briefly, and you can probably even look it up if you want to. So I'm going to show this to you. And you can find this in Wikipedia if you want to. The method of characteristic is actually a pretty simple one, okay? So you normally consider a differential equation like this. So it's more or less what we have here. So C, the derivative of some function C with respect to X times a function A plus this derivative times a function B is equal to some C. In our case, C is 0. So it's even more simple, okay? So you can consider this in a geometric way in the following, in a geometric fashion in the following way. So we take this here, dc over dx, dc over dy, and minus 1. So if you consider the solution C and consider like a surface graph, so C is C of x and y, in our case it's T3 of x2 and x3, we could consider this like some kind of surface, okay? So this looks probably something like this. This is some kind of banded surface. So the normal vector to this surface, if you remember this from your math classes, this is the normal vector of the surface, okay? And then if you take these functions A and B and C, then this differential equation in geometric terms tells us that the normal vector of this surface might look like this, should always be perpendicular to the vector field, because the inner product, this is what we see here, is simply the inner product, so it should always be 0, okay? And how could this be done? We can do it in the following way. Solve the partial differential equation in such a way that instead of finding this surface graph, we find a number of curves, a bundle of curves running through the surface, okay? So if we are able to find all the curves, the set of all curves running through this surface, we have equivalently solved the partial differential equation. So this is the way how it is done, and it's called Lagrange-Chapit equations. So we simply parameterize our unknown function C in terms of a parameter T. So obviously in this case, the derivative, these are the derivatives, and we simply call them A, B, C, and D. And in this case, in this way, we solve it. So this is, if you want to look it up, and I just promise you, in our control course, you will not have to solve this in such a complicated way. And then in our case, it's much more hands-on. So if we take our function T3, which is here, we find that this equation has to be satisfied. So in our case, we parameterize. Let's just solve this hands-on. We parameterize our function T3 by a new variable which we call S. Okay, and then of course, if we take the derivative with respect to our x2 and x3, we get dt3 over ds. It's dt3 over x2 times dx2 over ds. We take dt3 over dx3 times dtx3 over ds. And obviously this should be 0, okay? So the characteristic curve is such one that somehow runs along our solution T3, which is some kind of surface. And of course, it also has to satisfy the differential equation. And now everything becomes pretty simple, because if you take this equation here and compare it to that one, you see obviously that this derivative here should be equal to Vg. This derivative here should be equal to minus x3. And what you did here by this very simple step is you somehow transform this partial differential equation to a set of two ordinary differential equations that depend on S. And I would recommend that you try this at home. You have to solve both differential equations, obviously, which is an easy task. This is very easy. And then what you also have to do is you have to eliminate S, okay? So you have to eliminate S. And then you find this as a solution if you want. So this is what you have to do, okay? And there's our transformation. And now everything else that you're going to see in this example is just following the book. So we have, my pencil just seems to stop working right now. Let me just, I'm sorry, I have to stop this and restart the application. So it won't let me use the pencil for the moment. So let's just wait and do without. So this is our transformation, T3. And then everything else just follows the book. So we have the external and the internal dynamics. We get the control law. And this is all done by the book. And then, of course, we use some numerical values. Very importantly, also in this example here, we find that the internal dynamics, I can only show you by magnification because my pencil somehow stopped working, unfortunately. The internal dynamics is stable and it's linear also in this case. So C3 dot is equal to minus Vg to the minus 1 plus times G times C3. So you can see it's linear, obviously, I'm sorry, and it's stable, okay? Then we apply some control law. I'm skipping the rest. This is, maybe you consider it some homework to also to play around with it if you want to. And then obviously we get some results. So this is the height of the spacecraft. So we start this final descent at an altitude of say 2,500 meters. And then it takes about 200 seconds or 3 meters to make this soft landing. And then obviously also you see here the height. You can see that the height, the velocity of the spacecraft. So it eases down and gets a very soft landing. And then this is very important. This is the change of mass. So you see, it starts pretty heavy. So it's almost 9,000 kilograms. And then you end up with, say, about 7,000 kilograms when you land the spacecraft. So this is how it is done. And also very interesting, you see the U of t. So you can see at the beginning, there is some sort of pulse that happens, maybe probably just to slow down the descent. And then we have this very gradual descent. Just give me a moment. I'm just trying to wake up my pencil. Just trying to do this. Okay. Our pencil works again. Okay, so this was all about almost the systems with internal dynamics. So you can see whenever you have internal dynamics, you have to solve exactly this problem here of the partial differential equation. So it was pretty nice and easy here. It might be a lot more complicated with other systems. You were probably only able to solve this by symbolic math solvers. MATLAB is able to do this, also Mathematica. So generally, we will try to avoid it, okay? But we have to face it. There's one workaround which I'm going to sketch right now. So this can be seen more or less like an addendum. And this is the so-called dynamic extension algorithm. So why is it called that way? And I'm going to show you by an example of the lunar descent module how it works later on. The idea of dynamic extension algorithms is the following: raise the relative degree of the chosen output. So once you have chosen an output, and remember today in the beginning of the lecture, I've just told you whether we are going to run into trouble or not depends on how we chose this output. If we choose another output to control, for example, in the spacecraft, if we want to choose to control the mass of the spacecraft, everything might be a lot more easy, but then of course we are going to crash on the surface of the moon. If we disregard the altitude, it's probably not the right choice, okay? So mostly you're bound with your choice of the output. And then let's again assume that we have a relative degree of theta. So our equation is going to look like this. And this Lie derivative is going to be different from 0. So we have a relative degree of less than 1. So the key point and the key point in dynamic extension is very simple. It's simply to introduce a new state variable, which we call xi here, and somehow relate it to this derivative. Okay. It's shown here by a very simple procedure. We choose our input u, which is also seen here, and you can already see this is one guy which is not very nice, and we try to get rid of it. So we see in our control law, we just place this in the denominator. So eventually, when we're going to insert it, it's going to cancel out. And then we choose some polynomials, p and q, which obviously depend on x, and q is multiplied by xi. Okay, so far so good. This is not going to make a lot of progress with us. However, if we take u, insert it into here, then we are left with this equation. So that the derivative of the output, which we see here, is controlled by this. So we will try to get rid of this as well. Then our unknown polynomial p and q of x times xi. So to make things easy, we proceed in the following way. Just choosing red again. We take p and choose it exactly equal to this. So by this way, that's simply going to cancel out. And then the q of x, we choose it equal to 1. And in this way, we get a very simple relation. We see the derivative of the output y theta is equal to xi, our new and still unknown state variable. So you see the trick that we made is the following. Let me show you again. We took the control law, and again, this is a nonlinear control law. It depends on the state x, but it also depends on the new state, which we call xi, and we don't know anything about it thus far. We only know that we have to use it, and if we do so, and if we choose those polynomials properly, we get a very simple expression of this derivative of the output. And then we proceed in the simplest of all fashion. We take the derivative of xi and call this our new synthetic input. And by doing so, as you see here, and this is the result, and this is the reason why we call this dynamic extension, we see that we have increased the relative degree of the output by 1. So the output, the theta plus first derivative of the output is now controlled by our virtual input. Okay, so you see the trick is actually pretty easy. Everything that follows now is a little bit more complicated in terms of expressions that we have to deal with, but that's the basic idea. Okay, introduce a new state variable, put this new state variable to the control law, choose the polynomials wisely, such that we get this very simple expression for the output, carry out the derivative, and call it a new synthetic input. Okay, and now, of course, the relation between v and y is again a chain of theta plus 1 integrators. This is the way how it is done. However, there are still a few things that have to be solved. Okay, first of all, let's look at the extended system. The extended system is like this. So you see, this is our original state equation. And using this control law, it looks like this. So you see, we have the state vector, and I might call this x, for example. So this comprises x and xi. Okay, and obviously xi is used here. And then we see that the actual physical control input has disappeared. It's somehow contained in this control law, and this is our new extended system. So it's an extended system. So what we need now is the control law. We already have it almost, and we have to have a state transformation. Okay, so how do we go about the state transformation? Again, and now for the sake of simplicity, we just assume that the relative degree is equal to n-1. So not in order to make things more complicated, in the scriptum and in the lecture, I'm just treating this case. And if you want to treat more general cases, then you can actually look it up in the literature. You can find it very easy. So we assume that the relative degree is just n-1. So we have to increase the relative degree by 1. So what are we going to do? We are going to use everything that has already been, which is already true and tried. So we use these transformations, y is h of x, y dot is lf h of x, and so on and so forth, until we end up here in the last transformation. So we see y theta is equal to this guy. We already had this before. And we just say very simply that this is our transformation. So in this case, with the dynamic extension algorithm, we just put up with the situation that we have the input u in the transformation. So here I'm going to show you how to handle this. We tried to avoid it before, but now we are going to take it on board, and we see how what are the consequences. Okay. So the essential equation is the essential question is, how are we going to determine the input variable? And now this is the remedy. If you want to, things become a little bit more complicated. In order to do so, we take we actually take this equation here. So this is our equation that relates a certain derivative, in this case the nth derivative of the output, to our virtual input. We assume that we know this, and now we have to relate it to the actual physical input. And how do we do this? We take this derivative and we compute it by the book. So we have to take the output, we have to take exactly this equation here, and we have to carry out the time derivative. So we have to take this guy here, take the derivative with respect to x, and multiply it by x dot. And then we have to take this one here, and just bear in mind that this is a product. So it comprises of this expression here and this one here. So we have to apply the product rule. So first of all, we have to take the derivative of this with respect to time. So it's found here, times u. And then we take this one here and take the time derivative of u. So you can already see what is going to happen. We have u and u dot. So we are going to end up in a differential equation for u, okay? So those derivatives, they are simply computed and then expressed. So I'm going to skip this. But all in all, if I summarize everything, we can see that we get something which depends on u, some expression that depends on u squared, obviously. Then we get something which is u dot. So it's a little bit complicated, I would say. And then eventually we remember that this one here, this guy, is simply equal to our, to our chosen virtual input. So if we bring things together, we see that we have v, and then we get everything that we computed here. Maybe you can try this at home, but I'm just trying to point out here, we get u, we get again u, we get u squared, and we get u dot. So obviously what you see here, this equation is a differential equation for u, which is driven by our virtual input. So if we solve it for u dot, it looks like this, okay? So it means it's a little bit more complicated. In all the other cases that I've shown you today and also last week, it was pretty simple. Once you know v, you also know u. You also knew nu. Maybe let's just go upstairs, back in the equations, and I'm going to show you one of the examples just to point out what I mean. There's one. There would be one of these examples. So if you know v, the virtual input would be here, for example. You also know u. This was an algebraic equation, so you didn't have to solve differential equations. But here, I'm going back. In this situation, unfortunately, it's no longer like this. You have to solve a differential equation. This is the remedy, if you want so. And of course, you know, when you solve a differential equation that depends on time, you cannot rely on the fact that it's going to result in a stable solution. So not always. So you have to check this. And again, this depends on the so-called internal dynamics. If the internal dynamics are stable, then so is the so will be this differential equation here. Okay. Yes. So let's go back to the propelled spacecraft descent. So we had this problem here. We had the external dynamics, which is here, and of course, you can compute the Lie derivatives if you want so. So obviously we had a third order system, but we were only able to compute derivatives of the output until the order of 2 without getting the explicit influence of U. So we have this one here. And this is where we are going to start. So we have an order n is equal to 3, I'm sorry, it's 3. Theta is equal to 2. So we have to raise the relative degree of the system by 1. So we have to take this and carry on with the differentiation. So obviously here, V, the virtual input V, is the third time derivative of the output, which we set here. So if we take this, and if we carry out the time differentiation, you might want to do this. So y3 is equal to, it's equal to minus vg times x3 squared times x3 dot times u plus vg over x3 times u. And we know that x3 dot is simply, it's equal to minus u. So if you take this all together, you end up with this expression. So this is already this complicated differential equation that we had here. So you see, I'm really, I really like to show you examples which are pretty simple and where you could probably or easily compute everything by hand, and you can check at home whether this exactly corresponds to equation 545. So this is the more formal way, textbook way. Try it yourself, take the Lie derivatives that you probably need and compute them all. So you see there is some LF, LG, LF to the theta minus 1. So it's a little bit more complicated and out of the ordinary. But my homework would be check whether this is equal to equation 545. Okay, you have the Lie derivatives at hand. And you should end up with this one, okay? Okay, there are the Lie derivatives, so you can check this. And then there is our differential equation for u, and then you have to check whether it's stable, okay? If you look at this, we know u is actually our m dot, so the amount of mass that is sent out to the system. And if you look at this more closely, you can see there are two parts that might affect stability. This is V, which is our external virtual input that goes in here. And then, of course, there's X3, which is the mass of the spacecraft. So let's assume that X3 is always greater than 0. Of course, the mass should be greater or equal than 0. Then we have to observe that U is always greater than 0. So there's no way that we can actually suck mass into the jet and into the rocket engine. This is not possible. And if you consider this, obviously then this differential equation is stable. Okay, as long as u is greater than 0, so you can see there's a square here. So u squared is positive. If u would be negative, the story would be different. Okay, so then it would probably become unstable. Okay, but in this case, because this is not possible, we have a physical system with a physical meaning, it's not possible. Yes, we can put a check mark here, okay? And then let's turn to the state transformation. So this is y dot, y double dot. It's like this, so it's a transformation that depends on x and u, okay? That's the inverse transformation. And what we have to do is, in order to use the system, to use these equations, we have our reference virtual input V. We have to solve this differential equation. This differential equation is going to tell us what u is going to be. And from knowing u, we are able to determine the transformation all the time, and also the inverse transformation, okay? So this is how this is solved, and this is the dynamic extension algorithm. So you see, we avoid solving the partial differential equation, and it comes at a price. And this is in order to compute the control law, the physical control law. We have to solve a differential equation, and we have to check whether this one is stable before we apply it. Okay. And of course, there's some results, and of course, they're exactly equal to the ones that we have seen before. Okay. So this is more or less all about feedback linearization, which I want to show you. And now I'm going to turn to a new chapter, which is called control Lyapunov function. So it's again nonlinear control theory. And control Lyapunov function and control Lyapunov theory is about control laws. They might be nonlinear. So there's some U of X and D. You can also see this U is boldface. So we might as well consider systems with more than one input variable. It's not considered explicitly here in this lecture, but the boldface here is just used to indicate that, that we are in the nonlinear world. So what is a Lyapunov function? And let me just show you who Lyapunov was. Lyapunov functions are generally named after this guy, Alexander Mikhailovich Lyapunov. He was a Russian. He was Russian, and he was a mathematician. And he was actually studying dynamics of systems, so dynamics of mechanisms. And he had to give, you probably see it here, he had to give a course on the materials, on the dynamics of material points. Okay, so this was the way how he entered into his research. And then this actually led to his stability theory of Lyapunov. And I think it was probably inspired by something which I would like to show you in terms of a video, which is actually here. Let's start with this one here. You probably know what this is. This is a so-called, I'm just trying to figure out how to start the video right now. This is a funnel donation box. You probably know it. This is from Tiergarten Schönbrunn, but you can find it all over the place. This is if you want to donate for the animals, for example, you normally put it into this funnel, and then you probably like to play around with the coins. Let me show this again. So whenever you toss a coin, it does something like this, and we probably all know by experience. In any way we toss this coin, eventually it's going to end up in this sink here. Okay. Of course, it's thought for the children who like to play, and if you toss the coin in a normal way, eventually it's going to end up in this funnel. There's some other video which I'm going to show you, and we all know by experience this coin takes a very strange trajectory, so it goes up and down and up and down. And let me show you again. I'm not going to start this. This is a little bit strange. So it might go up and down and up and down. You see this, but eventually it ends up in this sink here. So we might want to ask ourselves the question: well, which of the trajectories that we are using here are actually going to end up in this funnel? Or in other words, are all the trajectories that we use, are all the ways that we are going to toss the coins here, are going to end up in the funnel? And obviously, from a physical consideration, the answer is obviously no, because if you just throw it in at a very high speed, it's going to be ejected out of this funnel on the other end, and it's not going to work. But essentially, Alexander Lyapunov probably asked himself the question, well, and you see this in this video here, there are so many possible trajectories that the coins might take. Are they all going to end up in the funnel? This was probably the question that he asked himself when he gave this lecture. And obviously, we know by experience that they're all going to end up in the funnel because of friction. And as I told you, as I've shown you from this Wikipedia entry a second ago, let me show you this again. It was probably inspired by dynamical systems. And each of these coins has two types of energy, and you can observe this very easily here. One part is the kinetic energy, and the second part is the potential energy. And as each of these coins surrenders its potential energy, it becomes faster and faster and faster. Okay, you can see this here. So the more they're going down and entering the sink, the faster they become. Okay. So probably Alexander Lyapunov thought that when we look at such a coin here, so there's the coin, you can hardly see it. It has two types of energy. This one is the kinetic energy. So this is probably the mass of the coin times its velocity squared half. And then probably if we relate the potential energy, so this is then like m times g times some height, okay? And then he probably found out that once the coin is in this funnel, the overall energy of that coin is equal to its mass times velocity squared half plus m times g times h. And then he probably observed that as time progressed, the change in that energy, it's probably m times v dot plus m times g times h dot. This is less than 0 because there's always some friction in the coins, okay? And this was probably his initial thoughts when he started with his Lyapunov stability theory. So he thought, okay, if a mechanical system probably has some friction in it or some mechanism that extracts energy from that system, then there's no other way for that coin as to eventually go down into the funnel. And probably if there's a lot of kinetic energy at the moment, the coin maybe takes that way. So it takes a longer time, but eventually all of these coins are ending up in the sink. This was probably his initial theory. So first of all, he was a mechanics guy, but he was also a mathematician. So he thought, well, is the overall energy of a mechanical system the only way we can prove stability? Because essentially the systems might look differently. You might have electrical systems or any other sort of system. So he generalized this idea of stability theory and came up with a very nice theorem, if you want so. He proposed a function which is now known as the Lyapunov function. And this function must have, it's actually very simple. It must have a minimum at the equilibrium point, so probably like here. And secondly, the function must decrease in the neighborhood of the equilibrium point along all trajectories. So no matter how we toss these coins, they should all end up here in the sink, so to say. So this is the basic idea, and this is his mathematical result. Let me just read this out to you. So we assume that there's a differential equation, x dot is f of x. So this is the equation of motion of this coin. Whenever a coin is tossed into the funnel, we assume that its equation of motion is given by this. There's an equilibrium point, which is the sink here in the funnel, of course. And then we assume that there's a neighborhood of the origin, okay? And there's a continuous and unique solution for all initial values within a neighborhood. And obviously, when we look at this, whenever the coin is tossed within this guidance here, then probably there will be a solution. If you toss it here, the very high velocity is probably going to be thrown out of the funnel, and then we can assume that probably there will be the U1 neighborhood somehow like this, okay? So normally it's always limited where this works, so to say. So we assume that the value of the Lyapunov function in the origin is 0, okay? And then there is a second neighborhood, which is within that first neighborhood U1, okay? And within there, we assume that the Lyapunov function is always positive, and its time derivative should either be always less or equal than 0 or less than 0. And then if we're able to do that, if we're able to find such a function, then the equilibrium point, the sink, is stable in the sense of Lyapunov. It's stable in the sense of Lyapunov if we have the equal sign. Now I'm going to choose a different color, or it will be asymptotically stable if we have this here. Okay, so this is the Lyapunov stability theory. So you can see this is not limited to the mechanical energy of a system. So you might find any mathematical function that satisfies all those conditions, and then you're able to prove stability. Very importantly, you'll probably not be able to see this from this theorem here. You don't have to solve the differential equation to prove stability. Okay. So when you look at all those coins being tossed here, you might think that we have to solve the differential equation for all possible trajectories, for all possible initial conditions. But the nice idea about Lyapunov theories, you don't have to do this. and it ends up in the so-called direct method of Lyapunov. It's called direct method because you don't have to solve the differential equation. I'm going to show you how this works, okay? Before we do so, there's one thing which is also important. You've seen that in the video example that I've shown you, we had this funnel, and of course the funnel was limited. It's not infinitely large. There are some systems, though, where we can prove that when x goes to infinity, so if the absolute value of the state vector x goes to infinity, then also v of x goes to infinity. We call this radially unbounded. So if this Lyapunov function is radially unbounded, and then the equilibrium point is globally stable. So it means no matter where we start in the state space, it will always, the state trajectory is always going to converge to the origin. Okay, so this is the nice thing that we would like to have. So let me show you two examples. Let me start by figure 6.2. So there's a number of trajectories that I'm showing you here. And obviously it indicates that they're all going into the origin. So just by inspection here we see, if you just draw a number of trajectories, so you can solve them numerically, for example, or by hand, we see that they converge to the origin. And this example here is probably more related to this funny donation funnel, because you see here trajectories that are actually closed. And by a coincidence here, we see v of x is c, so the Lyapunov function is such one that its contour lines are actually closed circles. So we choose this like a paraboloid, for example. And by coincidence here, the state trajectory here runs along the contour lines. In this case, whenever we solve the differential equation, we will see that the Lyapunov function is constant, okay? So we don't like this because obviously in this system, the energy is not decreasing. For example, if you take a very simple system, which is like the mass and spring system, and then of course, we have x, which is the deflection. So the state vector x1, let's call this x1. So the state vector would be x1 and x1 dot. So if this is an undamped oscillation, then the state trajectories are going to look like this. And if you choose the Lyapunov function that way, you will see that the energy in that system is not going to decrease, okay? So let's point out how we actually prove stability. Let's assume that we have some function v of x, and we call this a Lyapunov function candidate, okay? And then in order to look at the time derivative of the Lyapunov function, we simply take the gradient and multiply it by x dot, which is very closely related to the Lie derivative actually, okay? So you can use it, prove it with Lie derivatives. So you can see, if we know the state differential equation, which is given here, then everything becomes pretty easy. Then let me just point this out. You will see v dot is equal to the gradient of v, which depends on x, times f of x. So you can see it only depends on x. So this is some function let's call it gamma of x. So you can see very clearly that you don't have to solve the whole state differential equation. Probably you're not even able to do this, but you can only check along throughout the state space whether this time derivative is less than 0. Okay, it's either like less than 0 or less or equal than 0. Okay, so this is the reason why it's called the direct method. It's you use the differential equation directly. You don't have to solve the state differential equation. Okay, and then there's something else you might have noted this before. It makes a difference whether we have v dot is always less than 0 or it's less or equal than 0. Okay, and obviously in this case here, v dot is always equal to 0. So there's no way we prove stability. In this case here, obviously, v dot is always less than 0. However, there might also be systems that have a trajectory that might look like this. Let me show you something. It comes from the outside. Then it does this. So it's tangent to the Lyapunov function contour line, but only in one single point, and then it continues to converge to the origin. So in this case, it would be like v dot is equal to 0, but it's only in one point. And here v dot will be less than 0. And also here, v dot is less than 0. So you can see v dot is 0, but it's only in one particular and one single point, and it's not 0 along a whole trajectory. So you have to differentiate between the case where v dot is 0 along a trajectory, or where it's only 0 in one single point. Because you can imagine, if we only have this situation, we do not really care about it. If it's just 0 in one single point, we can disregard it. However, if it's 0 for a longer point, along a certain trajectory, it might cause trouble. This is the reason why we make this very distinct differentiation. And you can also see it here. V dot is continuously identically 0. This should not happen, okay? Then we have a problem, okay? And this is the more precise formulation of all this. This is the theorem of Barbashin and Kraskowski, okay? So again, we have a differential equation with an equilibrium point, xs, which is in the origin. So it's always, I have to mention this, it's always in the origin. If it's not in the origin, then you just transform it. You would just say, okay, x tilde, for example, that's x minus x0. So if f of x0 is 0. So if the equilibrium point is different from the origin, you just do something like this. So this is not normally a problem. Okay. Then we have the neighborhood. Okay. I probably have to talk about the neighborhood as well. Okay. Then we have the continuous partial derivatives. And then, of course, the Lyapunov function should be always greater than 0. And then we have the time derivative, which should be less or equal than 0. We tolerate that there is some equal sign, but it's only in particular in isolated points, but not on a trajectory of x. And then the equilibrium point is asymptotically stable, okay? So what we see here is that we have some initial value, which is in a neighborhood, which we call is U1. And then within that neighborhood, there's a second one, which is normally smaller than U1. And within that neighborhood, those conditions have to be satisfied. We will see later on that in most we have a so-called region of attraction, so which means that we have stability in the sense of Lyapunov, but only for certain initial conditions. Okay, this is very important to note also. Okay. And again, if the Lyapunov function is radially unbounded, already mentioned that, and if U2 is equal to the whole state space, okay, which is not often the case. So in most physical practical systems, this is not true, okay? Then the equilibrium is globally asymptotically stable. So mathematicians, when they work with Lyapunov stability, they always strive to prove global asymptotic stability. For us as control engineers, this is not it's not always possible, or it's only possible to prove global asymptotic stability in rare cases, unfortunately, okay? Also, only in rare cases, the trajectory runs continuously on the level curve of the Lyapunov function. So the situation that I've shown here is only happens in rare cases. So if there's v dot, if there's a v dot which is equal to 0, it normally happens as the trajectory traverses the contour lines, and it only is tangent in one isolated point, which we can tolerate, obviously. So all that said, it looks very nice and neat. So we have a Lyapunov function, we compute its derivative, we apply the direct method, which was here, where we prove whether this is always less than 0, or everything is nice and we're happy. However, there are two things that we have to consider. First of all, there was no control input yet. I have to return to this later on. So for example, for this part of the chapter, we're only considering autonomous systems which are not controlled by the outside. This will be a second part. Secondly, how to find the Lyapunov function. I've just shown you this coin example, and obviously a good Lyapunov function was the overall mechanical energy of the system, because we know there's friction, so the energy is going to decrease, it's going to be dissipated, and we know what is going to happen. However, in general control systems or general dynamical systems, there is no immediate guess as what kind of Lyapunov function we should choose. And there are, of course, many mathematicians and approaches in how to find Lyapunov functions. And this is really the very problematic part in Lyapunov stability. You have to find a Lyapunov function. And if there is any like particular given mathematical system, and there is already one example here, then even if you try very hard, and if you don't find any Lyapunov function for that system to prove stability, it doesn't mean that the system is unstable, okay? So the Lyapunov function is not finding a Lyapunov function for such a system is not a necessary condition for stability. However, it's a sufficient condition. So Lyapunov stability is a very strong stability theory. If you find a Lyapunov function, it's a sufficient condition for stability. However, it's not necessary. There are many systems which are not stable in the sense of Lyapunov, but they're still stable. So this is the thing that I have to mention. But before we start with that, let me show you a very simple illustration example, which is that one. So you see it's nonlinear, it's autonomous, so there's no input u. So we have an x1 dot, which is equal to x1 times x2 minus 1, and x2 dot is x2 times x1 minus 1, okay? So you can see obviously already from inspection of these equations before we apply any mathematical theory, let's assume, for example, that x2 is greater than 1, okay? What you can see here is then obviously that x1 is going to grow exponentially. Then x1 dot, like x1 dot, will be equal to x1 times some constant, which, and this is always greater than 0. Okay, so it's going to either grow or decrease exponentially. Now let's assume at the same time that x1 will be greater than 1, and then in this case x2 dot is equal to x2 times some constant, let's call it k2, which is also greater than 0. So also x2 is going to grow. So you see, obviously, if x1 and x2, if they're both greater than 1, then we can expect that the system is going to be unstable. And for the opposite case, we have to examine this. And then obviously there are two equilibrium points. It's either like this, that x is 0, so this is the origin, and there's another equilibrium point which makes this right-hand side 0, which is this one, okay? Now, it's always good, if it's possible by any means, to have your computer draw some trajectories, which I did here. So you can see here, there's one equilibrium point here at the origin, there's the other one, and as I've told you before, if x1 and x2 are both greater than 0, let's just shade this here. This is this area here. If they're both greater than 1, sorry, if the x1, x2 greater than 1, we are in the region of instability. And you can see this from the also from the trajectories, regardless of where they start, they're just going to infinity. So this is unstable and it indicates exponential growth. From the other trajectories, it's more or less obvious and suspicious that this will be a stable equilibrium point. And also you can see that by looking at the trajectories, we chose the Lyapunov function to be one which is one with radial symmetry, or more concretely, we chose it to be that way. So it's constant along circles, so to say, okay? It's obviously radially unbounded, okay? And of course, we have to check whether this makes sense. We take this Lyapunov function, we take this state differential equation, and now we have to check whether the Lyapunov function decreases along each of these trajectories. So obviously, just by inspection, it's very obvious that this is going to happen. But of course, we have to check it mathematically. So what do we have to do? We take the time derivative. So it's the gradient of v times x dot. So it's the gradient is obviously 2 times x1 and 2 times x2. And x dot is taken from the state differential equation, which is here. So it gives us this expression here. And you can see obviously that this is less than 0 if x1 and x2 are both less than 1. So if both of them are less than 1, it will be less than 0. if this is not the case, we have to undergo further examination, but it will be for sure if both of them are less than 1. So if you might check this at home. For example, if x1 would be like, for example, 2, then this expression would be 1. And then of course this expression is greater than 0, okay? And then obviously it depends alone on x2 whether this is still less than 0 or not, okay? So obviously for this region here, we are not quite sure what is going to happen, okay? So for example, if then x2, for example, if it shows x1 to be 2, so we would be here somewhere, then obviously we see that there is some kind of limit trajectory where we still get a stable behavior, but it's a little bit cumbersome, so to say. And if x2 is smaller and smaller, the system will be stable. Okay, so this is some way how you would work with Lyapunov functions. Okay, and then of course there's always some limit. So this is something which we would call the region of attraction. So for sure, if both x1 and x2, let me just highlight this here. If they are both less than 1, we're in the happy. This doesn't work. We're in the happy region. Obviously, everything is stable, but you can see by inspection that there are also some regions here where we are still going to be Lyapunov stable, but we have to pay attention. Okay, so this is the somehow critical region, so to say. This is how it works. Let me just conclude today's lecture by some I would say generic way, and this is something which is used in control theory very often. I just told you before that using or finding Lyapunov functions is the real cumbersome part in Lyapunov stability. It was very obvious and easy here. Very often in control theory we use quadratic Lyapunov functions. So we have a state vector which might be of arbitrary dimension, and then we choose for the Lyapunov function to look like this. So we choose some matrix R, and this matrix must be positive definite, okay? So mostly we choose positive, we choose symmetric matrices R, which are positive definite, which means we normally denote this by like this. R is greater than 0. It doesn't mean that all entries of the matrix are greater than 0, but it means that X transpose Rx is greater than 0 for all X which are where the absolute value of X is greater than 0. Okay, so for any choice of X, this should be greater than 0. Then we call R the positive definite matrix. So obviously this is a very nice Lyapunov function because it satisfies this one. It's greater than 0 if X is different from 0. And the contour lines normally look like this. So they are normally ellipses depending on the matrix R and its eigenvalues. You get this ellipsis, and then normally you're able to prove stability. And let me just show it by a very simple example, which is again a linear one. So X dot is equal to A times X. And you probably already know from earlier parts of the lecture that if all the eigenvalues, so if I of A, you normally denote it, the real parts of all eigenvalues of A are less than 0, then the system will be stable. Okay, let me just show you again how would you normally solve the differential equation. You would just write X is equal to some U times E to the lambda t, okay, and then X dot is equal to lambda times U E to the lambda t, which is equal to A times U to the E lambda t. So obviously in this case, A times U is equal to lambda times U. This is how you normally solve the differential equation. Probably have heard this in your math classes, in mathematics lectures. So whenever we find that the real part of those eigenvalues are less than 0, the system is stable because we know all trajectories are going to end up in the origin then. So how does this look like when we apply Lyapunov stability? So Lyapunov's direct method. We choose some matrix R. We don't know which one to choose for the moment. And then we compute the time derivative. So the time derivative of the Lyapunov function is this one. So just bear in mind that this is the product rule because we have a product here. And then we end at the right-hand side. So this is A times X for X dot. And for X dot transpose, we get X transpose times A transpose. And if we summarize everything, we get yet another matrix, which is this one here. And we denote this by Q, okay? And obviously Q also has to be positive definite. So Q has to be positive definite. And this is what we normally call the so-called Lyapunov equation. It's this one here, okay? So we say A transpose times R plus R times A should be equal to minus Q. And you could read this equation in different ways. One way would be, let's assume we have a certain matrix A, and we have chosen the matrix R. We have chosen it by some way, and then we have to check by inserting it in the equation and reading it from left to right, whether this matrix Q is positive definite. Or you could do it the other way around, which is a little bit more complicated. So we assume, we choose a different color, that we assume that A is given, and we assume that we want a certain matrix. We prescribe how fast should the system decay, so to say, and then what is the necessary R. This is a lot more difficult. This is the so-called Lyapunov equation. You can have MATLAB solve it for you. So if you're using MATLAB at home, you can actually use, there's a command, I think, which is called lyap. Or you can also look it up in the internet, how to solve the Lyapunov equation, and then you will get something like this. If there's one thing is, if matrix A is stable, so if it's Hurwitz, if all its eigenvalues, if the real parts of all its eigenvalues are negative, then the system, then you will find a solution to this Lyapunov function. This is one important result. This is the Lyapunov equation. And this is one way how we work in control theory, which we use quite frequently. So we ask ourselves, so there's a matrix A, we choose a certain matrix Q, so we want a certain rate of decay. You could imagine, for example, if Q is positive definite, and if it's very big, it means that the rate of decay, the rate at which V dot decays, is very strong, very big. Question is, are we going to find a certain R that satisfies the equation? This is the way how it is done. Okay. Okay, so I'm actually done with my lecture today. Let me just give you an outlook of how we are going to conclude, because thus far we have only considered autonomous differential equations. There was no word about how we are going to use it for control. So next week, I'm going to clarify something which is the domain of attraction. And then there's a number of examples, of course. And then next week, we are going to turn to control Lyapunov functions. So the question will be, let's assume that we have chosen a certain Lyapunov function candidate, and now we have a differential equation where there's also an input u. And then the question is, in order to satisfy this, so if we want v dots to decay, to decrease over time, what is the condition on u? So if we insert this into the time derivative of the Lyapunov functions, for example, what would be the infimum? What would be the control u where we get the strongest decay? That would be a typical equation, a typical question that is answered by control Lyapunov functions. Or otherwise, if there is a certain state feedback law, it might look like this. We might be able to check by these equations whether it's stable in the sense of Lyapunov or not. And of course, there are also some theorems and definitions that are going to give an answer. But this is subject of next week's lecture. So I'm done today. Thank you for your attention. And of course, I'm still open for any questions if there are. So everyone is still there. Well, if there are no further questions, then I say thank you again for your attention, and I'm going to see you back next week. All right. Because of the test, there was one question. So there was one question from Ali because of the test. Could you specify that?
I have a question.
Yeah.
Do you know what we have to do because of the test?
Yeah. The problem, I get this. The problem we are facing right now is we are right now the university is planning to open up the lecture halls for tests. However, first of all, they are only going to assign those tests that already have been missed, so like scheduled exams that should have been taken like in March or April. They will be given precedence, and then later on we will be informed when or how we are going to get a lecture hall for this test. So there's a variety of options. One of them being we are actually admitted to the seminar room, for example, that we can hold a test. However, there are very strict regulations in place as to like distance and maximum number of students in the room. And I'm afraid that this will be a problem. The other option might be that we are going to have an online test, and we have to decide it in the course of next month, because obviously the university is following the guidelines from the government. If the guidelines from the government are actually loosened, then we will have a chance of having just a normal exam. If not, then we will have to take different measures. Okay. Is there anyone here in the audience who will need their Zeugnis or the grade somewhere like in July? Is there anyone here who depends on getting the grade, the Zeugnis? But you can also let me know by email if there is any urgency from you. There's some message going in. Yeah, or Nuria Livovic. Yeah. So Mrs. Livovic, when do you need your Zeugnis? Okay, I mean, you can tell me later on. If there's any urgency, this is what I'm trying to say, is we will find some solution. So nobody is going to depend on that we are actually admitted to the lecture hall. Okay. Good. Any other questions from your side? So Alexis Benadier's, beginning of July. Yeah, this is okay. So I think it's going to unwind in the course of next month. So if we find that it's going to be difficult for you receiving the certificate, you just email me and we are going to find a solution. Okay. One last thing. There is a number of examples, especially the lunar landing, which we have covered today, and Alexis Benadier is going to distribute this to you, or I think he's already done this, so you're going to receive this. And again, I recommend take this, play around in MATLAB, okay, and just get acquainted, get familiar to all the operations, to the equations, and I think it's very important to just play around and see how you're going to get along with this. This really helps in also like solving exam problems, of course, because simply you have to run it and you have to get some experience with it. Okay. Good. So thank you again for your participation. What about the lab? Okay, the lab exercise. This is also one thing. The lab exercise, it's normally done online. I have to check this with Christoph Hamed now. It's either that we are admitted to the lab, so we will be able to run it. If this is the case, then everything is going to run as scheduled. If not, I'm going to give an additional lecture, like here with Zoom, where I'm going to explain you how this lab experiment works. So we have to be flexible in this. We also have a new nice lab experiment, which we'll then also show to you. So in any case, we will try to give you also this real world experience, so to say. And again, we have to be flexible due to the measures which are now in place, and we have to wait. And I think by mid-May, I expect that everything should actually settle and we know what we are up to. Okay. Good. So thanks again, everyone for attending, and I'm going to see you back next week. Bye-bye.